6. This will not be part of our exam. During the second hour, I'll open the floor for questions on any practice problems. We did not get any new practice problems last class. And so I'll open the floor for practice problems on all the sections and talk a little bit about the exam. Okay, so section 8.5, we were talking about power series. And the idea of a power series is that a power series is an infinite series with a variable in it. Now that's not really a good technical version. I mean, a true power series is a series of the form, the sum where n goes from 0 to infinity of Cn x to the n. And so if I were to write this out, we'd have a number plus a number times x plus a number times x squared plus a number times x to the third plus dot dot dot. And I would keep going. So the reason that this is called a power series is because the variable is raised to a power, and that power is the value that is being incremented by our sum. And so the big question that we want to ask here is, because we have these variables in here, once we get an example of a power series, we want to ask the question, for what values of x does the power series converge? And we looked at one example last time that was 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus dot dot dot. And because this particular series happens to be set up just right, that the C0 is 1 and the C1 coefficient is 1 and every single one of our coefficients is 1, then I can look at this series and say, hey look, this is set up just like a geometric series, and it's a geometric series with a equal to 1 and r is equal to x. And so as long as our r value is between -1 and 1, as long as our r value, the size of it, is less than 1, then this series converges, and it converges to a over 1 minus r, which in this case is 1 over 1 minus x. And so the sum 1 plus x squared plus x cubed plus x to the fourth plus x to the fifth plus dot 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 equals 1 over 1 minus x when x is between -1 and 1. And so this is a really, really, really good series to know. All right. Now that was the only example that we looked at last time. Today I want to look at a couple more examples of some power series, and maybe some power series that are a little bit stranger, even stranger than this one that I have written up here. Are there any questions about this particular example? Okay. All right, so let's look at a new example. And this one is the sum where n goes from 1 up to infinity of -1 to the n times x plus 2 to the n over n times 3 to the n. All right, so I look at this thing, and as soon as I know things that I notice are that I have a series, and as part of this series, I have this variable x inside here. And so the weird thing is that, number one, that we have x plus 2 raised to a power. That's not quite like this power series that I have written here, but we had a second version of that power series that was, if I wrote this as the sum of where n goes from 0 up to infinity of Cn times x minus a to the n, then this is exactly like this one over here, except for now instead of x, we have x minus a's. And so this was a power series centered at x is equal to a. And so this is a second version of our power series. The only difference between this guy and the one over here is that now we have x plus or minus some number in there. So when I look at this power series, I can look at this and say, I've got x minus a number. Well, I see a plus up there, so I would really want to rewrite this as x minus a negative 2. And so this is an example of a power series centered at x is equal to negative 2.
That's just because you rewrite it to look like x plus 2.
That's right, that's right. So really this is x minus a negative 2 because I want to have it in the form x minus the number I'm looking at. Okay, so this is our power series centered at x equals negative 2. The question that we want to ask is, for what values of x does our power series converge? All right, so that means that I need to look at the series and say, all right, I need to use some kind of a series test on this thing. Now, as I look at this series, I see a few things. I see an n that's in the base, but I also see n's that are in powers. Now, the negative 1 to a power, I don't really care about that particular power, but I do want to focus on this power on the x plus 2 and the power on the 3. It turns out that when we have a power series, every single power series will always, always, always have an x raised to the power of n, or an x plus 2 raised to the power of n. So we're always going to have an n in the power. Now, whenever we have an n in the power, what's a good test to use?
Ratio?
Yeah, the ratio test is the test we're going to use. So whenever we're talking about a power series, we're going to be using the ratio test. Now, the ratio test says that I want to look at the limit as n goes to infinity of the n plus first term divided by the nth term and take the absolute value of that. And we want to evaluate that. And if this value turns out to be less than 1, then the series converges. If this value is greater than 1, the series diverges. And if this value is equal to 1, then we know nothing. All right, so let's set up this ratio test and see what happens. So I've got my limit as n goes to infinity, and I'm looking at the entire term here. This is my an. I'm covering up the series sign, and I'm just looking at the term itself. And everywhere that I see an n, I'm going to replace that with an n plus 1. So we've got negative 1 to the n plus 1 times x plus 2 to the n plus 1 divided by n plus 1 times 3 raised to the n plus 1. I'm going to take that and I'm going to divide it by that entire term, but exactly copied as is. So we have negative 1 to the n times x plus 2 to the n over n times 3 to the n. Are there any questions about setting that up? Okay. So after I've set this up, then, and I don't really need to necessarily write this very first line, because as soon as I write this down, I'm immediately going to multiply by the reciprocal of my denominator. So my next line is going to look like the limit as n goes to infinity of negative 1 to the n plus 1 times x plus 2 to the n plus 1 divided by n plus 1 times 3 to the n plus 1 times the reciprocal of this bottom part, so times n times 3 to the n over negative 1 to the n times x plus 2 to the n. And I still have my absolute value bars. Okay, I'd like you to take about 10 seconds and turn to your neighbor and tell your neighbor one thing that you can do in here to start simplifying this bulky expression that we have here. Just one thing. If you didn't say at least one thing, it is too late. If you've said more than one thing, then you've gone above and beyond. Okay, so what is one thing that we can do here to start thinking about simplifying? Any suggestions?
So you could write negative 1 to the n times negative 1.
Okay. Negative 1 to the n times negative 1.
And you can do that for the...
Okay, wait, you only get one thing. All right, other ideas?
Or to look at where you have a plus one, that just gives you can cancel out.
This one here? Wait, you say it a little louder, so I can't hear you.
So, you have your 3 and plus 1.
Yep.
You just leave that 3.
Yeah, so this 3 to the n plus 1 we can write as 3 to the n times 3 to the first, and that's going to cancel with our 3 to the n up top. Okay. Anything else? Jeff?
You could do x plus 2 to the n times x plus 2 to the 1, right?
Okay, x plus 2 to the n times... Uh-oh, I didn't leave enough space. X plus 2 to the first.
Right.
Okay. All right. Anything else that we can rewrite?
Could you do the same thing with bottom for the n plus 1 times 3 to the n plus 1, carry that?
This one here?
Yeah, that one there. Carry that, the 3n plus 1 all the way through to the n. And
Oh, so
1.
do n times 3 to the n plus 1?
Right.
I actually want to maybe avoid doing that, because if I do that, then I have two separate terms that are added together, and then suddenly I cannot cancel anything with stuff up top. So I'm actually, it's better for me to leave this as multiplication of two separate things. Okay, yeah, so I think we're about done with all of the adjusting that we can do. Let's fill in the rest of the terms. We've got our n plus 1. We've got our n times 3 to the n over negative 1 to the n times x plus 2 to the n. And all of this is inside absolute value bars. So now that we've rewritten that, some really nice things happen, and Mike mentioned this, that we really don't need to rewrite 3 to the n plus 1 as 3 to the n times 3 to the first. We can look at these two and say, hey look, there's n plus 1 of these 3's on the bottom and n of them on the top, so that leaves us with one of the 3's on the bottom. So this middle step, maybe we need to write it out or maybe we don't, that's totally your preference. Some other things that cancel, negative 1 to the n, x plus 2 to the n, and we are left with the limit as n goes to infinity of negative 1 times x plus 2 times n over n plus 1 times 3. And I still have the absolute value bar.
Is it important to keep that negative 1 since it's an absolute value? Could that cancel also?
That's a really good point. Because we have this absolute value bars, I can actually eliminate this negative 1 as well. Okay, the absolute value of negative 1 is 1, so let's just go ahead and get rid of that. We don't have to worry about that negative at all. So in fact, a shortcut way here is to say, hey, I've got absolute value bars. I don't care about negative 1 to the n plus 1. I could cross that off right away, and I don't care about negative 1 to the n. I'm not canceling these because they divide each other exactly. I'm canceling them because of the absolute value bars. Okay, so now we're left with this particular limit, and we're going to take the limit as n goes to infinity. Now, what I see in here is that I see n's, and I see x's, and I also see some numbers. I see a 2 and a 3 as well. And this limit that we want to look at is strictly about the n values. So in the eyes of the limit, some of these other terms, such as the x plus 2 and the 3, those are constants. I can pull them in front of the limit sign. And so I can write this as the absolute value of x plus 2, well, I should say x plus 2 over 3, and have the absolute value. Now, remember, if I pull it out in front, I cannot legally pull it out of the absolute value sign unless I carry that absolute value sign along with me. So I have this, and then I have the limit as n goes to infinity of n over n plus 1. Okay, are there any questions about what I just did here?
So you can't just ignore the absolute value since we canceled the negatives?
Right, so that's a good question. So I could ignore the absolute values if all I was pulling out was a 3, because 3 is always positive. But I don't know what value x has associated with it. So because that x is unknown, I have to carry along those absolute value bars. So another way that I could write this is that I could write this as absolute value of x plus 2 divided by 3. So I can ignore the absolute value bars on the 3, but not on the x term.
If it was just coefficients, you wouldn't need the absolute value.
That's right. If we just had numbers here, coefficient numbers, then that I wouldn't need the absolute value bars.
And will that affect, once you evaluate your limit, do you then have to multiply it by that value, or will that affect the whole greater than 1, less than 1, equal to 1?
This is going to affect that at the end, because once we take our limit, we're still going to have an unknown variable in here. We're not going to have to work with that.
So you can't put the absolute value bars just around the x?
So to say absolute value of x plus 2 is not the same as absolute value of x plus the absolute value of 2.
Right.
So I cannot do that. For example, if
Okay.
x
All
is...
right,
yeah.
right.
Yeah, okay. Yeah, think about an example where
Right,
these two
right,
sides are not equal,
right.
and that'll convince you. Okay?
Oh, what about the absolute value around the ends?
Oh, around the ends. So now with the ends here, when I look at these, n is certainly a positive number. We're talking about 1, 2, 3, 4, etc., even 0. So in this part, I really don't need these absolute value bars anymore. I put them in here because I was a little lazy when I think about it, but I don't. They're not required around this anymore. Okay. Other questions or comments? Sometimes you have to think harder to determine whether you want to remove them, and if it doesn't really matter, why bother thinking?
On the test, you wouldn't grade us off if we put it, they didn't need it, like right there.
Oh no, that's totally fine. No, that's not a mathematical problem. It's just you could get rid of them if you wanted to, but you don't have to. Okay. All right. So here we are, and we've got our limit as n goes to infinity of n over n plus 1. And so I look at this and I say, hey, look, the powers are the same on the top and the bottom, so I can look at the coefficients in front of my largest powers, and those coefficients are both 1s, and so my limit is equal to 1. So I've got the absolute value of x plus 2 divided by 3 times 1.
So can you do that infinity rule on that? Would that be the same as what you're doing?
Yes. Yeah, we're looking at highest power in the top and the bottom. If those powers are the same, then you've got that your top and your bottom are going to infinity at the same rate. And you want to focus on the coefficients in that case. All right, other questions or comments?
Would you get a similar answer if you distributed, so before you broke your limit up?
Mm-hmm.
If you distributed n, so you were taking the limit of nx plus 2n, 3n plus 1, or
So if we had looked at the limit as n goes to infinity of nx plus 2n over 3n plus 3, if I looked at that, this is going to be a little bit more of a challenge because suddenly I've got n going to infinity and my x is a coefficient on n. And you would probably analyze this in a very similar way. But what you would first do is say, oh look, I have n to the first in 2 different places, so I'd want to combine that into one term. And if I do that, then I have x plus 2 times n. So you're basically going back to where you started by doing that. Okay, so we're now at the end of our limit. We've taken it. Wow, that sounded very depressing. We're at our limit, and so we've taken the limit, and we still have this expression left. And the thing is that because we have this variable of x, this is not just a plain old number. If you're talking a regular series like the series that you're going to see on your exam on Monday, your final answer down here would be a number. And you could say, okay, is that number less than 1, if so the series converges? Is that number greater than 1, if so the series diverges? And if that number is equal to 1, then we're sad. So our question here is to ask for what values of x does our power series converge? And so we want this value to be less than 1.
So you just set it to 0 and solve for x?
Well, we're not going to set this equal to 0. We're actually going to set this expression, absolute value of x plus 2 over 3, we're going to set that to be less than 1. And so our series converges when absolute value of x plus 2 over 3, this is what we have right down here, is less than 1. And so we've got to solve this inequality for x.
3
So,
halves.
welcome to college algebra.
3
Alright, so to solve this inequality, the very first thing I would do is to maybe multiply by 3. Okay? Or actually, even before I do that, something, well, no, let's do that first. Let's do that first. Absolute value of x plus 2 is less than 3. Now, when I have absolute values and I have an inequality, what I want to do is set this up so that I can get rid of the absolute value bars. Which means that this expression in the middle, what absolute value bars say is that the size of this value has to be less than 3. Which means that the x plus 2 must be less than 3 and greater than negative 3. So this is one way I can get rid of my absolute value bars. Okay, so from here, I still want to solve for x, and so to get x by itself, I can subtract 2 from both sides. Well, both sides meaning all 3 sides. And so I end up with negative 5 is less than x is less than 1. And so we say that our series converges when x is between negative 5 and 1. And if I were to draw a picture of this on a number line, what I'm looking at here is x values between positive 1 and 1, 2, 3, 4, 5, negative 5. And so we are interested in this interval right here between negative 5 and 1. Now, one thing that you might notice about this interval, what number is exactly halfway between negative 5 and 1? Negative 2. So negative 2 is showing up right here in the middle. And remember, way back in the beginning of this problem, we said that our power series was a series that was centered at x equals negative 2. And so we can write this as center of our series is x equals negative 2. We can say that the interval of convergence is the interval where x is between negative 5 and 1. And another piece of vocabulary that shows up is that sometimes the question we've asked, what is the radius of convergence? And so our radius of convergence is the distance from the center out to the edge. So in this case, from negative 2 up to 1, we have a distance of 3, and from negative 2 down to negative 5, we have a distance of 3. And so our radius of convergence is 3. So those are 3 pieces of information that you might be interested in knowing about for this particular series. Okay, so we've just looked at this series. I'd like to actually, now that we've looked at this and said, okay, this series with this x converges between negative 5 and 1, what does that actually look like? And so I've got a Mathematica picture I'd like to show you. Sum of negative 1 to the n times x plus 2 to the n divided by n times 3 to the n, which is exactly the series we were just looking at. And so what these terms that are listed here, these are our partial sums. Okay, so we've got just the first term, we've got the first term plus the second term, first plus second plus third, etc. Now what's more interesting is to see what happens as we add more and more of these terms. So I showed you a couple of these animations before. But watch closely what happens as I hit play, or actually as I step forward on this series. Now, as we're stepping forward, you'll notice that that right-hand side is flipping up and down. That has to do whether we have an even function or an odd function. And our left side is just sort of slowly bending upwards. And so, as we move farther and farther along, it seems like our function is settling in, at least in the middle there. So I'm going to go ahead and hit play. And it's moving so fast now that it doesn't flip up and down at every single time. But what you can see is that right around -2, the function is always lying, it never actually moves right at -2. And as we move farther and farther along, as our slider moves to the right, let's go ahead and hit pause on this for a second. What we'll see is that this part that was kind of slowly creeping upwards stops at about -5. And this part that's flipping back and forth like a fishtail, well, that fishtail is starting at +1. And so outside of the interval from -5 to 1, our function is doing all kinds of crazy stuff. It doesn't even show up over here, and over here it's flipping like a fish. But in between -5 and +1, this curve is settling in as we add more and more terms. So then that brings us to another question, and that is, okay, well, this series is converging to some function between -5 and 1. We've got this convergence happening. So what is this series converging to? Well, that, it turns out, is a hard question. But we can ask Mathematica. And so the next thing I'm going to do is I've typed in our series, the sum where n goes from 1 up to infinity of this series. And if I ask Mathematica to evaluate this, then I end up with log of 3 minus log of 5 plus 1. And Mathematica log is natural log. So it turns out that this particular series that we have converges to y is equal to natural log of 3 minus the natural log of 5 plus x. And so if I now graph both of these together, well, actually, first, this is a picture of natural log of 3 plus natural, or minus natural log of 5 plus x. Here's what that function looks like. And if I superimpose them on each other, then I can watch as my function, in fact, matches up with natural log of 3 minus natural log of 5 plus x, but only between -5 and +1. Outside that interval, all hell breaks loose. All right, any questions or comments about that?
Is the log of 3, is the 3 the radius?
Um,
Why that's there?
It seems like that could be a reasonable thing to think about. Again, yeah, I would do a couple more examples of this and see if that pattern continues.
And then I'm just trying to think of like the application of this. Would this be helpful if you were trying to precisely integrate something on like a certain range, and then if you could find something that just happens to match up, you get a precise answer?
So that's a really good question. So we're kind of working backwards at this point. Given a series, we might ask, what does that series converge to? But more importantly, what's going to happen is that we're going to start out with some weird function that we maybe want to integrate, or maybe want integration in particular, or that we may want to approximate. And so I'd like to be able to take some funky function, maybe even funkier than this one, and write that as a power series, and use that power series to approximate the function, maybe cut it off after the 3rd term or the 20th term, depending on how good I want my approximation to be. I can use that power series to do stuff like integrate, which is way easier than integrating some maybe really weird function that I have over there. So right now we're kind of working backwards, but that's our next step, is to give ourselves a crazy function and write out its power series. Good, other questions? Going once, going twice. Okay. So let's look at one final example of a power series. And then we'll take our 10-minute break. The computer always, or the overhead always asks you if you're sure if you want to turn it off. And then it wouldn't let me turn it off. Okay, final example on power series. We've got the sum where n goes from 0 up to infinity of 3 to the n times x to the n over n factorial. Alright, so I'm given the power series. The question is always the same. For what values of x does this series converge? And more specifically, I might be asked to find the center and radius of convergence. Okay, so I look at my power series up here, and I can answer the first part about the center right away because I see that I have x raised to the n. I don't have x minus or plus a number. So my series is centered at x is equal to 0, and I get that because I have just a plain x to the n as opposed to x plus or minus some number to the n. Alright, so to answer the rest of the questions, I need to perform a test that involves series, and the series test that I'm going to perform is the ratio test because I've got x raised to the power of n, so my n is in the power, and I have an n factorial, and so both of those are signs that I want to use the ratio test. Power series, I'm always going to use the ratio test. Okay, so I'm going to write down my limit as n goes to infinity. And I'll plug in my n plus first term, so I've got 3 to the n plus 1 times x to the n plus 1 divided by n plus 1 factorial. And then I'm going to divide by the nth term, but that's the same thing as multiplying by the reciprocal, so I'm not going to bother writing that first line. And I'll just have times n factorial over 3 to the n times x to the n. Okay, any questions about writing that part down? Okay, so I've written this out now. Now I need to do some simplifying, so I can rewrite a couple of the terms. 3 to the n plus 1 is 3 to the n times 3 to the first. X to the n plus 1 is x to the n times x to the first. And this n plus 1 factorial, remember that we can rewrite that as n factorial times n plus 1. So all of my rewriting happened on the n plus first term. The nth term I'm just going to write as n factorial over 3 to the n times x to the n. Okay, any questions about that part? Rewriting about the n factorial or any other part about it? Okay. So now I can start canceling. I can cancel the 3 to the n's, I can cancel the x to the n, I can cancel the n factorials, and we are left with the limit as n goes to infinity of 3x over n plus 1. Alright, so I want to evaluate this limit. But in order to evaluate the limit, I'd like to get rid of some of the pesky terms. Really, the only one that really concerns me is this x. So I'd like to pull that out in the front. I might as well go ahead and pull the 3 out in front as well. So I've got absolute value of 3x times the limit as n goes to infinity of 1 over n plus 1. in the absolute value bars, I don't have to worry about having the 3 inside the absolute value bars, but I must have the x inside the absolute value bars. And the 1 over n plus 1, I don't need those absolute value bars anymore either. I can get rid of those as well. Okay, so now the limit as n goes to infinity of 1 over n plus 1. What happens to 1 over n plus 1 as n gets really big?
0.
Yeah, this thing goes to 0. And so what we end up with is the absolute value of 3x times 0. And anything times 0 gives us 0. So the question now is, for what values of x is 0 less than 1? All of them, yeah. So in this case here, 0 is less than 1 for all values of x. So our series converges for all values of x. So answering the question of find the center and the radius of convergence, well, our center is x equals 0. And our radius of convergence is infinity.
Would it be plus or minus infinity or just
The-
infinity?
Well, so the radius is, like on our last example, when we had -2 up to 1 and down to -5, the radius was still 3 no matter which direction we were going. Okay, so that concludes that example. Are there any questions about that? All right, so it turns out when you are looking at these power series and you want to know how far out from the center does the series converge, well, one of 3 possibilities can occur. So for a power series given by the sum where n goes from 0 up to infinity of Cn times x minus a to the n. So we've got a power series, we've got coefficients, we have x minus a raised to a power, so we're set this power series centered at x equals a. We have 3 possibilities. The first one is that the series converges only at x is equal to a. And that would happen if, for example, in this particular series, if the limit as n goes to infinity, if that limit went to infinity and there was no way that you could no matter what x value you chose, you're never going to have a value less than 1, that's when you get this first possibility. The second possibility is that the series converges for all values of x. And in that case, we might say that our radius of convergence is equal to infinity. And the third possibility, and then I'm getting a little bit low on the board over here, so I'll write it over on the left. The third possibility is that we have some specific interval on which our series converges. So the third possibility is that the series converges in some radius r about x equal to a, and diverges elsewhere. And so what I imagine in my head for this one is that I have a number line, and here is A on the number line, and there's some distance away from A going to the left and to the right, that's a distance of r, and our series converges everywhere within that interval, within that radius of r to the left and to the right of our center, and then outside of that interval the series diverges.
So what is an example of one again? I'm sorry.
So an example of one might be if let's say we had gotten to this scenario here, and instead of 1 over n plus 1, it was actually the opposite, it was n plus 1 over 1.
So it would be infinity?
Yeah, we would, if we ended up down here with a value of infinity, infinity is never less than 1, no matter what x value you choose, and that would be a scenario where the first one would happen. Okay, so these are the three things that happen. And so as far as power series goes, what I'd like you to be able to do is to look at a power series and use the ratio test and determine what is the center. You can get that even without the ratio test, but find the center and find the radius of convergence. Okay? And so those are the two things that I'm going to ask you to do. Now, there is a question that comes up, and that is, what happens at these endpoints? These endpoints are where whatever x value we get makes the ratio equal to 1, and with the ratio test we know nothing. And so if we were super excited about these endpoints, what we would have to do is say, okay, let's say that this endpoint was a 1, for example. I would plug 1 in for x and evaluate that series by itself, and I'd plug in -5 if that were our other endpoint and evaluate that series by itself. So if you were super excited about these endpoints, you'd have to evaluate those separately from the rest of this example. Today I'm not so excited about or interested in the endpoints, but if you are interested in them, then you could evaluate those separately. Okay, so here are the practice problems, and these are practice problems I'd like you to look at, but maybe wait until after the end of studying for your exam.